Alright, this video is about curve fitting with quadratic models, and we are going to model data, and we're going to use our models to analyze and predict results. So, first of all, recall that you can use differences to analyze patterns in data. For example, for a set of ordered parts with equally spaced x values, a quadratic function has a constant non-zero second differences, as shown below. So if they give you values in a table and the x values are equally spaced on top, you can subtract the y value, you can subtract the output values on the bottom, and if the second difference is the same, then it's quadratic. Okay, and if the differences are not the same for the second difference, then it's not quadratic. So let's look at an example of that. Let's determine whether this data represents a quadratic function. To do that, we have to find the first and second differences. So first of all, we need to make sure that the x values are equally spaced. So here this goes from 1 to 3 to 5 to 7 to 9. So it looks like it's plus 2 each time on top. The x values are evenly spaced. So now I'm going to subtract the y values here and to see what my first differences are. So 31 minus 17 is 14, 17 minus 7 is 10, 7 minus 6 is 1, 1 minus negative 1 is 2. So those are my first differences. When I subtract them again, each of the differences is 4. So since I got the same difference each time for my second difference, that means that this function is a quadratic function because the second differences are constant for equally spaced x values. Okay, how about this one? We need to find the first and second differences in order to determine if it's a quadratic function. So first of all, the x values are in fact equally spaced. They're going up by 1 on the top line. And on the bottom line, when we subtract them, 81 minus 27, 54, 18, 6, 2, these are the values we get for our first differences. However, when we subtract them again, the second differences are not the same. So since the second differences are not all equally spaced, this is not going to be a quadratic function because the second differences are not constant for equally spaced x values. Okay, one more of these. Let's look at this one and find the first and second differences. Looks like the x values are each going down by 1. Well, when I subtract my first differences, I've already got a number that's the same. So since my first differences are giving me the same number each time, that means that the function is going to be linear. My second differences would just be 0. So the function is not quadratic. The first differences are constant, so the function is linear. Okay. Now, just as 2 points define a linear function, 3 nonlinear points define a quadratic function. And those 3 points do not have to be evenly spaced, but they do have to be nonlinear. So collinear points lie on the same line. Nonlinear points do not all lie on the same line. So if you are given 3 points, okay, and they are not all on the same line, then you can fit a quadratic function to go through those 3 points. A quadratic model is a quadratic function that represents a real data set. Models are useful for making estimates. So previously you've learned how to make a linear regression through 2 points, and today we're going to use our calculators to make a quadratic regression going through 3 points. So here's how we're going to do that. Here's an example. The table shows the cost of circular plastic wading pools based on the pool's diameter. Find a quadratic model for the cost of the pool, given its diameter. Use the model to estimate the cost of the pool with a diameter of 8 feet. So here we have 4 different diameters are given to us, and for each diameter they've given us the cost that goes with that diameter. So what we're going to have to do is take this information and enter it into our calculators. You're going to get to this screen, enter the data in your calculator by pushing Stat button, and then after you push Stat, number 1 is going to say Edit, and when you push that Edit, this is a screen that's going to come up, and on the screen you're going to enter the data from the table here. So under L1 you're going to list the x values, and under L2 list the y values. Once the data is in your calculator, then you're going to make a quadratic regression. In order to do that, you're going to push the Stat button, and you're going to scroll across the top of the screen to Calc. And then number 5 has Quadratic Regression, and that's what you're going to use. And you're going to push it. It's going to give you this information that's going to come up. This tells you what your function is. So you're going to use ax squared plus bx plus c, and the a value in there, they've given you the a value, they've given you the b value, and the c value that make that equation true. So that is, that's the formula, that's the equation that we're going to graph. And then this r squared value here is telling you how closely the formula is actually fitting the data. So 0.999, that is really close to 1. That means that this is a really good equation. This means it's a really good data fit for this data. So good. So you're going to take the equation that you just got, and you're going to go ahead and graph it. And when you graph it, you should see it go through the points that you've already plotted. Okay? And now we can just use the table function, as we've been doing, to determine the answer to the question. So use the table to find the value of x at 8, and you can see that when x is 8, from the table we have 49.538. Okay, so that's going to be their answer. Okay, the coefficient the coefficient of determination, r squared, shows how well a quadratic function model fits the data. The closer it is to 1, the better the fit. In a model with 0.996, which is very, very close to 1, the quadratic model is a good fit. And that's what I was explaining a second ago. All right, so we've got our answer then. We've taken the function that they gave us when we did the quadratic regression, and we put in the values for a, b, and c, and we got our function. Okay, when we graphed it, and we used the t-table to see that for a diameter of 8, the model estimates a cost of about $49.54. All right, great.